BCR 2.4 is all about looking at ionic and covalent structures and comparing and contrasting them. So, looking at, we've already talked about how they bond, we've bonded them, and now you're taking a look at how they physically how their structures physically look. And you did this through the activity of ionic and covalent structures where you were making structures out of marshmallows. So the sodium chloride structures, you were making it out of two different color marshmallows and marshmallow fluff. And the covalent structures, you were making them out of white color marshmallows because we were only talking about carbon and toothpicks. So, big idea questions that were hit in that activity, going to be hit on your performance task and kind of covered here are as follows. How do real life ionic structures stick or bond together? Ionic compounds can be infinitely large. How can this be? How do real life covalent structures stick or bond together? How can the same element bond with itself but have different variations of strength and flexibility? And we're specifically looking at graphite and diamond because we created those structures. How are ionic and covalent compound structures similar and how are they different? So, if we take a look at ionic first, ionic, just as a recap, it is a cation and an anion bonding with each other. And how that happens is the cation, which is typically your metal, gives away all of its valence electrons to the nonmetal, which is the anion. And it does this to both obtain a full outer shell. So, the example of lithium fluoride. Lithium has one valence electron. It is going to get rid of that and it actually gives it to fluorine, which has seven. When that happens, lithium has no valence electrons now, but it is full because the previous shell is full, and fluorine now has full valence electrons because it now has eight. So when this happens, and this is where the bond occurs, when this happens, it becomes lithium plus one because it got rid of that electron, and fluorine minus one. Because opposites attract, that's where the bond occurs. That's why these things stick together. And we represented that through the marshmallow fluff. The marshmallow fluff was that attraction. So think about magnets when you're thinking about ionic. Opposites attract, and that's what sticks them together. And that occurs because the cation gives its valence electrons to the anion to create opposite charges. Now, the second point here is these things can be infinitely large. So if you think about the activity, you guys made sodium chloride. The first one I just made you make one sodium, one chlorine, and bond it together. Then I had you do 4 sodium and 4 chlorine, and you kept on adding to that structure. And I could have asked you to do that over 200 times, if not more. We could have made one as big as the whole entire room. Little redundant and probably a little wasted time, but we could do it. And if you take a look at these salt mines here, that's what occurs. It just continues to follow that pattern of plus minus, so that we can create these massive structures. Now, ionic structures are more cube-like in structure. The reason being, as long as you're a positive, you can attract any negative in any direction. And it's not going to be just a one-dimensional direction. It's going to be 360 degrees. So that's why you're going to see most of them are going to be cube-like in structure. And that's why I instructed you for sodium chloride to be more cube-like in structure, because that's more real-life application. Than just making one big long line of sodium chloride compounds. And when you see sodium chloride, or when you see ionic compounds in nature, you will find that they're more cube-like in structure too. So they follow this pattern, this very rigid pattern that you're seeing here on the screen of these structures. Now, covalent structures are different. These take two anions and they share their valence electrons. Both, again, getting a full outer shell. And the example here we have is H2O. Okay, so if you look at oxygen originally has 6 valence electrons and hydrogen is 1. And what they're going to do is they're going to share this pair of electrons here. And when they share that pair, when that occurs, you will then have that bond. So the bond occurs because they're sharing it. And in class, we represented that as you guys holding hands with straws in between you. And those straws represented your valence electrons. Now, these as well can get big. And we'll talk about that more in the next the next slide. But if you take a look here, this diamond, okay, as long as it's following that diamond pattern, again, which we'll see, they can get big, but they are just a little bit more restricted by their structures because they have to follow a more rigid pattern than positive, negative, positive, negative. And you can see that here. So a single diamond structure that you should have created looked like this one, okay, this big picture. Then a double diamond right here. Okay. And then we had some students go above and beyond, and this structure is not even comparing some of the other structures that some students made. Some of the students made above 10 diamond structures. So like they combined all of these structures together, and there was over at least 10 different diamonds, if not more, in one structure. And that's not that big, but it does follow the pattern. So as long as it follows the geometric pattern, then it can be as big as we want it as well. Just a little bit more restricted though. So things that you can see here, like graphite, again, following the pattern, diamond. If we follow that pattern, we can still create bigger ones, just like you saw in the last one. And then there's something called like a buckyball. Here, the weird thing is carbon, because of its number of valence electrons, and four is a massive number for bonding. Because it has 4 valence electrons, that means it has pretty much endless possibilities of bonding with other things and with itself. And I think the stat is over 10 million different bonds can be formed through that. So we have things like graphite, okay, carbon, but it looks more hexagonal in shape. Again, weird word, and whatever. Anyway, and then we have diamonds. So if you go back and look at this, you're dealing with all of these triangles. Because you have different geometric shapes, you're going to have different flexibilities. You're going to have different strengths, and that's useful. Like diamonds, we use them in obviously for rare stones like people wear on their hand. You want to make sure that that's very durable so it doesn't break or anything like that. Also, we use it in construction. If we're trying to drill a hole, there's diamond head drills, or in something that's pretty like hard, like rock, granite, that kind of stuff. Same thing with saws. There's diamond head saws. Now, I want you to know that diamond, I know people say, oh, it's the strongest kind of compound. It's not. There is some things that are stronger, but it is high up there. Now, as opposed to graphite was very flexible, like you should have seen, but you should have seen it was very flimsy, easily to break. And think about why we use graphite. Graphite is what we use in pencils. So would we want something that's really strong in pencils? Probably not, because we're writing on paper. If we were writing on stone, sure, let's use diamond. But if we're writing on paper, we want it to break off, and that's what we can see. So there's just so many different forms of carbon for the simple fact that there's 4 valence electrons that need to be full. So we can do single bonds, double bonds, triple bonds, and quadruple bonds. And, on all of those, we can just, it creates a massive number of possibilities. So just as a recap, both of these structures are different in the fact that we have different patterns, different ways of creating them, different limitations, okay? But the biggest similarity between them is that they are taking 2 elements and chemically sticking them together, chemically bonding them together. So we have it could be the same element, as an example of carbon, or it could be 2 different elements with sodium chloride. But as long as you have these bonds, we are now taking one element, a single element, and bonding it with another element. And that is the biggest similarity between them. So please let me know if you have any questions, or if you have anything for me as you guys are going on to your performance task. Just as a reminder about your performance task, it is something that you are individually turning in. You can work together and have similar ideas. However, everyone needs to submit their own written responses in their own words. And that's a part of this. And there's many of reminders within the activity and within the assessment itself. So just be aware of that, and let me know if you have any questions. Good luck.